Recording in progress.
Welcome to this evening's High Spatial Public Lecture Series, which is a weekly series of lectures that the Aspen Center for Physics hosts. I am Sanjay Reddy. I'm one of the organizers of the Gravitational Wave program that's ongoing, and David is one of its participants. Before I introduce David, I want to briefly tell you a few things about the Aspen Center. The Aspen Center for Physics, now in its 60th year, brings to the campus here about 1,000 or so physicists from all around the world. The unique and informal setting that the Aspen Center provides us is great for incubating new ideas. And the center is a non-profit institution, and it has partial support from the National Science Foundation and from the Science Foundation, and we gratefully welcome donations from the general public. This public lecture series is named in honor and in memory of Heinz Beetles, who was a professor of physics at Rockefeller University and president of the New York Academy of Sciences, and a trustee of the Aspen Center, and a longtime member and participant of many of the Aspen Center's programs. He was a part-time local resident who tragically died in a climbing accident in 1988. And this seminar series honors his various contributions to the Institute. A few ground rules: we request that all participants at this event conduct themselves in a manner that is welcoming of all others and show respect and consideration, free from any form of discrimination, harassment, or retaliation, just so that we respect each other and respect each other's opinion. And if you have questions at the end of the session, please raise your hand, and David will be happy to address them. So now I'll go on to talk a little bit about our speaker today, David Schumacher, who is a professor at MIT Kavli Institute. David Schumacher is a research scientist, a senior research scientist at MIT. He earned 2 PhD degrees, one at MIT in 1980 for his contributions to the Kavli cosmic microwave satellite, another from the University of Paris in 1987 for contributions to understanding methods of interferometric detection of gravitational waves, which is what he'll tell us about today. He has served as the leader of the Advanced Ligo project, which is an instrument that's currently taking data, and he is a spokesperson for the LIGO scientific collaboration. LIGO stands for Laser Interferometric Gravitational Wave Observatories. He is a fellow of the American Physical Society and the American Association for Advancement of Science. He has shared the Austrus, Miller, and Gruber prizes for the detection of gravitational waves, along with the gravitational wave community. And he is one of the most instrumental people in putting together all the instruments that make these amazing discoveries that we're about to hear possible. So very delighted to introduce David, and again, this is going to be an exciting talk.
Thank you, Sanjay, for that generous introduction. Thank you to you people from Aspen for providing me with a wonderful place to spend a couple of weeks doing physics and wandering around a bit. Let's see, the meeting is being recorded by the hosts. Irma, you're going to have to hit the got button there. Let me say a couple of things about this first page here. First off, I really do draw very heavily on the resources of my colleagues for a lot of the graphics and so forth and so on. And if you look at this at some later time and you're really deeply curious, you can follow up on those things. I work for the Ligo laboratory. It's a Caltech MIT joint effort. I've been spending a lot of time working on the next generation of gravitational wave detectors. And you'll hear about that later on. This is the most important thing on this page. It's the National Science Foundation. It's the endeavor in the US that funds most of the fundamental science. They're an incredibly courageous and dependable, far-seeing organization. If anybody ever asks you if people do good things with the taxpayers' money in Washington, National Science Foundation is the answer. So with that, I'm going to start a story. The instrument will listen to me here. Let's try a different thing. We try thinking here once. There we go. Oh, long ago and far away, 1.4 billion years ago, 1.4 billion light years away, there are two black holes that were orbiting around each other. They'd actually been orbiting around each other for billions of years. At this moment, they're starting to get very close to the end of this death spiral. As they spin, they get faster and faster and closer and closer. And at a certain point, they actually touch and become one. But before they do that, they're shaking space-time with their masses being accelerated around each other. Once the system settles into this final black hole, it jiggles a little bit, and then it's still for the rest of time. I mean, also, if you can turn down the lights on the surface of the screen, it would be great. So moving forward, almost that full 1.4, 1.3 billion years, come now to recent times, 1609. We have, it's actually Hevelius and not Galileo. It shows some of the first use of a telescope as new technology to look at a brand new set of phenomena in the sky. And the reason that I call your attention to this, besides the fact that he was a great discoverer and ended up in jail because he was on the wrong side of politics at the time, it shows what can happen if you introduce a new technology to the human ability to look deeply into the universe. And with that, you know, not all that much happened in the first perhaps 100 years or 200 years. Today, what we do with telescopes is just amazing. There's some parallel, I don't want to overdrive it, with the new technology we have now, looks at a new messenger. He was looking at photons, looking at gravitons. It's a very exciting path, a very exciting moment to be looking at this kind of thing. Now let's move along another 80 years or so to what the story, which is probably not true, that Newton was hit on the head with an apple. I don't think he needed that encouragement to think about gravity and to start to codify rules for how objects behave, and to come up with a concept, which was that there's an attractive force between masses, draw them together. With the equations that he worked out, we're able to make predictions of all kinds and of great detail that were perfectly accurate for all of our observational needs and desires until a few hundred years later. And indeed, a few hundred years later, 300 years, along came Albert Einstein, a modest Swiss patent clerk, who I guess in his off time when he wasn't reviewing patents, was thinking about synchronizing clocks in different railway stations so that things could be delivered on time. Was Swiss after all, or he was in Switzerland. And also thinking about children throwing balls to each other while on a merry-go-round and wondering what the trajectory of the ball was and why it made sense that it did what it did. And somehow, in his brilliance, from those kinds of thoughts came a new model of how gravity works. His theory, general relativity, recast entirely this notion. You no longer talk about an attractive force between sun and Earth. You talk about the sun deforming space-time in a way that the Earth now rolls around this point of deformation in space-time. At the same moment, Earth is making a little dimple and the sun feels that. So it's a reciprocal relationship. Mass curves space-time, and space-time tells mass how to move. And with this concept, he was able to, first off, match all of Newton's predictions. So he had an idea that at least he had a theory that was good for that. He also made some predictions about what could else be observed that would show that his theory was accurate. And his idea was this. In general, you think of light, a star, taking a straight line to the Earth. His notion, though, was that, in fact, light is also subject to the same law that he discovered. It must curve along this curved space-time, like a mass would follow that very same trajectory. Happily, it was just about this time that a good eclipse of the sun was planned and was expected. And so a bunch of expeditions set out. And the nice thing about an eclipse is that you can look at stars very close to the sun without being blinded by the sunlight and see whether or not this effect is true. In fact, it was verified to great precision. His predictions from general relativity came through. And this is the first of a couple of New York Times front pages that I'll put up on the page here, the lights all askew in the heavens, men of science more or less agog with the results of eclipse observations. Einstein theory triumphs. So there was a good reason to think that Einstein theory was one that was actually correct for nature, or was a good way of predicting what nature would do, is a better way of putting it. Another thing that he predicted was the existence of gravitational waves. Here we're looking again at our black holes, a slightly different projection. You see once again these deformations in space-time underneath the black holes. And now we start to see some action around the outside. Also see down here a trace of time that shows the stretching and squeezing of space-time, the distance, which is what he was predicting was the effect of a gravitational wave. As again, once again, these two black holes work around each other. They're shedding energy in the form of gravitational waves, and that's why they're speeding up and getting closer and closer. What we see is that the amplitude of this wave is growing in frequency, it's growing in amplitude, and it becomes largest just at the point where these two black holes, their protective sheath inside of which light cannot escape, only becomes one. And at that moment, we have a big burst of gravitational waves. This thing wobbles a bit like Jello and actually makes some more waves. And then these waves start propagating out. And one of the features of his theory was that they travel at the speed of light. This, again, you can imagine having taken place 1.3, 1.4 billion light years ago. And now these waves are propagating their way to the Earth. The thing I want to note is that it was just about at that same time that monocellular living things on the Earth were becoming multicellular. So it's really fun to think about this parallel track of evolution on the Earth moving us toward who we are now. And at the same time, these gravitational waves from very far away racing toward the Earth. They're going to come together at a certain point. And so what kind of effect could we see on the Earth due to this passing gravitational wave? Stretching and squeezing in space. The gravitational wave comes down, zoom, across this, it's supposed to be a meter stick. I only had a yardstick in my house, so it was inches, but about the same length. This meter stick changes length. I think this is 1/60th. This is, I think, 18 zeros. A tiny, tiny, tiny fraction of a meter. This yardstick changes as this gravitational wave goes by. That's the measurable that we have on the Earth that we can use to sense the passing of a gravitational wave. Because this is a strain, right? If I had an exercise band, one of these things like this, I put two marks close together, and I stretch the band, those marks are not going to move very much. If I put the marks very far apart on the exercise band, with the same strain in space, those marks move a great deal. So it's a really important thing to keep in mind that the longer the distance over which you sense this passing wave, the larger the signal is, the easier for me as an experimentalist to make something that will actually succeed in detecting it. Einstein, in one of his papers in 1918, wrote about this. He made a calculation about what kind of amplitude of signal you could hope to find. And he came to the conclusion that with these numbers that are so small that one sees, that A, in almost all conceivable cases, must have a practically disappearing value. And he thought this was a curiosity. He thought this was a kind of theoretical outcome, which was so far from being measurable, that it didn't deserve much more thought. About 50 years later, Ray Weiss, he's a physics professor at MIT, been my mentor for the last 40 years or something like that, teaching a class in general relativity to a bunch of students. He's an experimentalist and an instrument builder. Wanted to find a way to connect these ideas to something real and give the students a sense of what it meant to try and make a measurement of this kind. At that time, lasers were just coming to be available. With this newfangled laser and some mirrors, he mocked up an idea, gave it as a problem to his students. They all got it right. He just kept on working on it because he thought it was a really cool thing. And so let me give you an idea of how that works. This is an animation, it looks like a luminescent sea snake to me, of the effect of a gravitational wave passing from right to left, say, and the effect on a ring of free particles is, as I was saying, stretching and squeezing, and squeezing and stretching. You can see that if you could measure the distance from here to here, minus the distance from here to here, you have something that was pretty sensitive to gravitational waves. Let's take that thing, point it down at the surface of what we would call an optical table, the surface on which you mount a bunch of optical components. You have here a laser, a mirror that splits the beam in two, a couple of mirrors out here, and something which turns light intensity into an electrical signal, a photodiode or something like that. So here's a little illustration of how this can work. The wave comes out, and we think of these as a wave. The wave gets split onto the two sides, onto the two arms of the interferometer. It comes back and recombines. Now, if the light beams have their waves aligned, that will be a very high intensity of light at the output. If they're anti-aligned, then there's very little light that comes out. And you modulate how much light comes out by making this differential change on the two sides. It's exactly the action of a gravitational wave. You imagine that circle, you imagine this beam splitter is stuck in the middle of that luminescent sea snake. It's going to see one arm shorter and one arm longer. This is the technique that he came up with as a way of getting at the signal. And I say again, if you make the arms 10 times longer, the effect is 10 times bigger. See that come back to us a bit later on. So this is my graduate student experiment. This is back in the 70s or so. And you can kind of make out, this is a prototype of one of our first efforts to build an instrument that could show where the problems were and how to move to the future. This is an argon ion laser. The whole thing is in a vacuum system with, these are these arms, which in this case are they're about 1.5 meters long, something like that. There's a beam splitter here, there's an end mirror here and an end mirror here. In a vacuum system so that the light as it travels won't be disturbed. As you know, when you see shimmering over the hot road in the summer, it would be a complete masking of the gravitational wave. So you have to have an excellent vacuum system. And then you hang the objects with a thin wire so that they've got some isolation from seismic noise. We did this kind of experiment in a number of different places around the world and collaborated together, competed sometimes, try to come up with the best ways to do these things. And after a couple decades of hard work, got to the point where we could propose to the National Science Foundation to build a full-scale instrument that could possibly make these kinds of detections. What you, the taxpayer, gave us, thank you, are two sites, one in Livingston, Louisiana, and one in Hanford, Washington. We have here 4-kilometer long, 2.5 mile long arms. And each one of those arms contains a vacuum tube, which is 1.2 meters in diameter to carry the laser light down and back. They're very powerful lasers that are used. There's a control system which allows us to keep track of where things are and to control them. And there are a bunch of young, enthusiastic people very excited about making the first measurement of this kind in the world. Those are the ingredients to make measurement. Here are a couple of still photographs so you can get a little bit clearer idea. This is in Louisiana. We had to build up a berm from the normal level of the earth so that it wouldn't flood. 100-year floodplain. I don't know whether it's 300 years now or 30. Of course, in Louisiana, you have to dig up some dirt, and when you dig up dirt and you make a pit, it fills with water, and it fills with alligators. And what you see here is a concrete bed, which is straight. That is to say, it doesn't follow the curvature of the Earth because the photons have to go in a straight line. You do some really careful GPS work. You lay down this vacuum system, you put a cover down. Take a little closer look at that cover, the concrete bed, 1.2 meters. This is concrete, and it's pretty thick. I think you might be able to see it's something like this. The thickness of that is determined by the most powerful bullets that we expect to have shot the thing. It's because it's a curiosity on the horizon. What do? Let's give a pot shot and see what happens. Well, it turns out, actually, the thing that it can resist is an SUV. This is up in Hanford, which is on a nuclear reservation site. And there they do midnight scrambles. You know, if there were a terrorist attack, you want to make sure that you'd be able to rile people up. And somehow this officer didn't have this thing on his map. The airbag served its purpose. The officer was completely uninjured, the car is completely totaled, and Ligo survived. So. This is what we have, another view of the Hanford and the Livingston observatories here and here. They're separated by 10 milliseconds if you're a photon, 3,000 kilometers if you're a bird. And it's the Ligo laboratory of Caltech and MIT that put these together, again, with NSF support. We built these observatories in the 90s. We observed with the detectors in the early 2000s. And what did we see? We saw no gravitational wave signals. We did learn how to build and commission detectors. We learned how to analyze the data. We created new upper limits and significant non-measurements. Somebody else saw a gamma ray burst there, and we did not see a gravitational wave there. Thus, it was not closer than such and such a distance, that kind of thing. It was clear that we needed more sensitive detectors. What was really neat is we had put this into our plan, the National Science Foundation, back in the mid-'80s, and the National Science Foundation signed up to the full dinner. And so we started to design. And our idea was this: we wanted to move from initial LIGO to advanced LIGO. It's a new detector in that same infrastructure. That money was not lost. The system will continue to be repopulated with new detectors time after time. The volume of space grows as the cube of sensitivity. If I'm torn about this pointer, I kind of like having a physical thing in my hand, but if you double the reach of an instrument from 1R to 2R, then you move the volume from 1 unit of volume to 8 units of volume. 4/3 pi r cubed is the rule for how much volume is enclosed inside a given sphere. So if we can double the reach of our instrument, the sensitivity of it, we get 8 times more signals. Well, we wanted to make a factor of 10 increase. And with that factor of 10, imagine if we'd seen 1 signal in our initial detector, we'd see like 1,000 here with this new larger detector. Well, in fact, we'd seen 0 here, which leaves a little question open how many we're going to see here. But we thought it was a good enough bet to make us move forward on the idea. Here is one of the photographs I'm going to show of the inside of this vacuum system. And it's a huge vacuum system. We send people inside it to service it. We're able to pull the people back out again before closing it up and evacuating all the air out. This is one of the mirrors that responds to the gravitational wave. It's about this big, about this thick, weighs about 100 pounds. It's one of the most perfect optics in the world, full optical system. Here's another view that optic is sitting here in front and looking down the 4-kilometer long tube in that direction. This is some fancy optics that we used to get the system initially going. There are a couple of bunnies. Well, mirrors have to remain extremely clean. And so everybody has to get completely suited up when they're in there. They're inside something like this. This is this vacuum system, which is that, there's the beam splitter, there's the beam splitter, there's the beam splitter. And to give you a sense of scale, I took a photo of Albert Einstein playing violin, and we scaled it to about the right height. Albert would come up to something like this. It's a really monstrous installation. It also has a complicated control system to allow us to get all of the mirrors pointing at each other over these mile-long distances, the tubes, and also to keep them from swaying back and forth and disturbing the measurement. You can see some of the things that we use to watch what's going on that way. So it was about, it was in early 2015 that we finished putting all of the instrument together. And so we spent about another 6 months getting the 2 instruments, one in Livingston, one in Hanford, to the point where they were working pretty darn well. And we said, well, look, it must be time to start to do an observing run to try and see if the thing is functioning correctly and to take data, practice taking data. So 1.3 billion years after the black holes merged and multicellular life started on Earth, 100 years after Einstein predicted this notion of these gravitational waves, 50 years after Ray Weiss came up with the basic concept of how the thing would work, 20 years after the NSF, MIT, and Caltech founded LIGO, this observatory to build the things, 10 years after advanced LIGO on the second stage of instruments, the OK, 6 months after we started doing our detector tuning, 2 days after we started observing, the first signal arrived. This is going to be a distraction. It's just a replay of that little movie that I had before. This plot here shows the stretching and squeezing of space. This is time, the 10th of a second from there to there. And you see two traces. One is the sorry, the dry air. This is the Livingston output. This is the Hanford output. What you can see here before the signal arrives is noise. They just jiggle around. And then you start to see the signal appear, that wiggle, that characteristic wiggle of a gravitational wave, and it dies down to zero. And it is exactly the picture-perfect prediction for what we would have expected from a gravitational wave of these two black holes. Now I want to, you may have even heard this before, we take the output of that photodetector that's looking at the light, we put it through an amplifier into a speaker. That way you're not hearing a gravitational wave really, you're hearing the light intensity on the photodiode turned into a sound. It's still really communicative. And I'm going to play you the sound repeated 3 times over quickly. And you'll see the graph will follow here on the plot, give you a sense of the evolution in time. And we have to remember what you're hearing here are two black holes, each about 30 times the mass of our sun, flipping around each other at in a hundredth of a second. An inconceivable thing. Whoop, it's the sound of that sinusoid that starts out slowly, speeds up very more and more, and then ends suddenly. And that's what we actually listen to the machine with earphones. It's a really good way to figure out what's working and what isn't. But that's what we saw when this gravitational wave passed. We were thrilled. Whoops. There we go. Here's my second New York Times headline. We were above the fold. I learned that terminology when we reached this thing. They gave us with a faint chirp, the scientists prove Einstein correct. This never proves something correct. It shows that it's not incorrect, but that's a detail. Yeah. And this is people installing baffles down this 4-kilometer long tube. You can imagine the kind of work that was. Anyway, we were absolutely delighted. And as you just saw, it led to the 2017 Nobel Prize, which was actually 2015 for the measurement, 2017 for the prize. Pretty quick. And the people pictured here, well, this is Ray Weiss. It's a little bit later on from what we saw in an earlier slide. Soren, an absolutely fantastic astrophysicist, Barry Barish, an absolutely brilliant builder. And the three of them really merited, I think, this joint prize. And it's nice the way that it spans between Ray's deep intuition and hands-on approach, the astrophysicist, theorist, and the builder. It takes a village, and these are the kings of our village. Oh, it's a fluke. We get lucky. We currently have about 90 signals. LIGO instruments also joined by a French-Italian instrument, the Virgo instrument. And this little plot here, there's no real meaning to the horizontal axis. On the vertical axis, the mass of the objects that are involved. And what we have in general are, everywhere, are two objects that come together to make a more massive single object. Two black holes make a single final black hole. We've seen some little tiny things. I'll talk a bit more about them. And also some really monstrous things which start to puzzle some of the astrophysics and challenge some of the astrophysical models. So from this, you can start to make population studies, figure out how many big ones and how many small ones there are, what their distribution and distance is. And you can also look for anomalies and strange and wild things. That's what really interests me. These are what I would call vanilla black hole events. We do have a second special event beyond that first one I want to mention. It involves neutron stars. A neutron star, black hole is a defect in space-time where a very massive object has collapsed down to the point where there's no volume left, the mass that's there. There's this thing we call the event horizon that's outside of it. which is the barrier between the places where light can still escape, even though it's passing very close to this massive object. If you go beyond that event horizon, you lose that information, hidden forever at least. A neutron star is a smaller star that explodes and collapses, but it doesn't collapse down to that point of nothingness. It collapses to something of incredibly high density. I think the number is something that a teaspoon of neutron star mass is the same as the mass of the 4 Great Pyramids or something like that. But it's hard to imagine how massive this is. And when made up a graph of this, my son now lives in Oakland, California, which is just underneath the neutron star there. What did we saw 2 neutron stars spiral into each other. This is an animation of that happening. And it's the same, I mean, basically the same story. They're still obeying Einstein's gravity. The difference with neutron stars is that they're made of real matter. When you get them that excited, give off light, give off gamma rays and visible light, radio waves. And that means that you have 2 messengers now, not just the gravitational wave, but also the electromagnetic waves. I'm going to play you another one of these clips. Now we have Hanford, Livingston, and Virgo, this French-Italian detector that's joined us. I'm going to guide your eye on the Livingston trace because it's the one where the signal is the clearest. And these lighter neutron stars take a bit more time to spiral in. In fact, I really want you to listen to the sound at the beginning of this, because it's the sound of the instrument when there's nothing going on except the noises and the jostling, both fundamental and technical, in the instrument. Nothing here but just fundamental noise, thermal noise, shot noise. But at a certain point, you'll start to see a trace appear. Clearer and clearer as the signal gets bigger and bigger. So that was the sound of this remarkable event. Sound, I say. It's the gravitational wave signal stretching the squeezing of space turned into sound through magic of electronics. Since we had 3 detectors placed here, here, and here on the surface of the globe, you can find out where the source of this signal's from. In fact, it first hit the Virgo detector, then the Livingston detector, and then the Hanford detector. By knowing that the signals travel exactly at the speed of light, and having the exact timing of arrival of these 3, you can calculate back to the head of the tripod and say, point to the sky, with some uncertainty about where it is. And I'm going to give you a little graphic of that. Oh, actually, no, first I have to say, as I noted, it's not only gravitational waves that were given off, there were also a lot of other things that were going on. The first thing that we saw was, well, here's our gravitational wave trace again. And then 1.7 seconds later, there was an event seen in multiple gamma ray satellites. These are very short wavelength, very hard, very well beyond X-ray photons. And almost simultaneously, and coming from the same place in the sky, we saw this. This means, let me show you this graphic then. This is going to show the series of localizations that we were able to do. One of the X-ray satellites called Fermi was able to say it's here on the sky. Fermi and Integral, 2 other instruments, say, well, it must be in this section of the sky, but the intersection between those 2. Then we take the best localization that we can make with the 2 LIGO detectors. That leads to a banana here and a banana here. Then you add in the Virgo measurement. You say it must be in this ellipse. We computed those coordinates and we sent them as fast as we could to our astronomical colleagues. They started to look at each one of the galaxies that were included in that picture. It only took, I don't know, half hour after night fell next to the instruments, they discovered one not very interesting otherwise galaxy. There was a new tiny point of light. And so here is that galaxy I just showed you. It's a photograph these folks are regularly scanning the sky and looking for changes, looking for transients. And we had scanned the sky here 20 days before the event. And at the event takes place at this little crosshair here. There's nothing there. 10.9 hours after we saw it, which was time for the sun to set and then look, this slope and a number of different observers were able to see this tiny pinprick of light. And so this was the proof that we've been able to make multi-messenger gravitational wave, gamma ray, optical, multi-messenger astrophysics observation. That allows all kinds of really neat conclusions to be made about the mechanics inside these events. Here, yeah, here's another graphic that shows, as always, the two objects that are twirling around each other. But what's really going to be cool is to watch when they come together. You'll see all of the stuff that's ejected from the system. There is energy and jets ejected from the top and the bottom. There's a great deal of the neutron star material which gets thrown off into space, which then recollapses into stable elements. What's really cool is that model is something that had been worked out years ago. I mean, not all that many years ago, but something that was astronomers, astrophysicists were pretty darn sure this kind of thing would happen. With this one measurement, these various different wavelengths, we're able to confirm many, many, many details of this model. One of the predictions of the model has to do with their periodic table, the elements of in nature. All of these lighter elements are ones that are familiar to us from the normal operation of stars. Stars do fusion. They start out with some helium, they burn it into, they start out with hydrogen, they burn it into some helium, the next higher, lithium and beryllium and so forth and so on. And all these elements in gray are ones that are pretty easy to fabricate in normal stellar operation. There was always a hard time describing the large quantity of the heavier elements, like iridium, platinum, gold, mercury, and so forth and so on. This model of the neutron star spiraling together provides an explanation for these heavier elements. All those neutrons that were being sent out collapse back down into heavy atoms like gold. Here's the really, really cool thing. Gold in the medal that the Nobelists received in 2017 was almost assuredly made in neutron star in spirals billions of years ago. It's so beautiful the way those things come together. So that's most of what we've done so far. What's next? We're very well rewarded with improvements in the detectors. Here's a little plot to show how that works for us. This is the number of events that we've seen so far. As I said, we've seen 90, and we've seen them in a series of different observing runs. And we make little improvements, or make improvements to the instruments between them. And you can see we made 3 detections in the first one, made some improvements. We got up to 8 detections in the second one, made some big improvements, and we added Virgo for the third one, and that's where things really started to take off. So we want to continue this to increase the slope of that trend. And we actually have to put some space between our various different observing runs to make those improvements. But we win it back quickly because of the numbers of events that we pick up. Oh, as I've said a little too often, you make the arms longer, it gets better. We want to take Ligo's 2.5-mile long arms, build an instrument with 25-mile long arms instead. That's the concept behind Cosmic Explorer. So it's this is our fancy logo. This is the ever important fact that the NSF is supporting us in this endeavor. They're clearly going to have to look very carefully and make a big ask to Congress if this is going to go forward. That looks like it's a possible path for us to succeed. This is this artist, actually, it's an undergraduate student at the Cal State Fullerton, did this nice mock-up of what we think the thing might look like. We've written a long document about it. If you're really excited, look up cosmicexplorer.org. You can find all kinds of documents. So it's the US contribution to the next generation gravitational wave network. Einstein telescope is what the Europeans are putting together. We'll be working together in the measure that we can. The LIGO-like concept baseline of two widely separated observatories, new ones, 48 kilometers and 20 kilometers. Turns out 20 kilometers is ideal for looking even more carefully at this neutron star phenomenon that I described to you. This Cosmic Explorer is a larger and more technically advanced version of LIGO. It's going to be using technology that's already shown to be possible in LIGO. We'll start out with detectors which are almost identical to the 4-kilometer ones in terms of really tricky parts, by making it that much bigger. Evidently, there are some complications that come in. But basically, the first detectors are very low risk, and we think that's an important thing to promise to anybody who gives us the money to build these things. One objective for Cosmic Explorer is to see all black holes and neutron stars throughout cosmic time. Here's what we call a donut plot. Imagine you're sitting in the center here, and the distance to which you can see is determined by the distance radially out from the center point. For black holes, the side of the plot is for black holes. We have seen so far at the level of this O3 observing run, and this is the sort of 90 or 85 or something like that, events that we've seen so far of black holes and black holes. With this instrument that we're talking about, Cosmic Explorer, we'll be able to see all of the black holes that coalesce in the universe over all to cosmic time, which are in the right frequency range to match our detector. It's I don't know, it's millions of events. For neutron stars, the story is pretty similar. We're currently just down at this point here where we've seen 1 or 2 or 3 of these neutron star in spirals. And with Einstein Telescope or Cosmic Explorer, you can see pretty much all of this field. So we think that this next instrument will be the one that will really draw the line on what you can do with these gravitational wave detectors. You will be surprised, but anyway, certainly we'll be able to see the majesty of the universe reflected in these dense objects spiraling together. Cosmic Explorer is big, in case you hadn't gotten that message yet. And there's a lot of, I mean, it can be difficult to find sites, but we can use automated systems to scour the maps of the US. Actually, what you want to find is that the light has to go in a straight line, right? And if you just put it on the surface, put this thing on the surface of a sphere, go 40 kilometers, you're either removing a whole lot of dirt in the middle or adding a whole bunch on the end to get a straight line. What we do is we search for things that people usually think of as called bowls. If you find the right bowl, it's actually not a bowl, it's just actually perfectly flat. And so there are, maybe it's not astonishing, but the United States has got maybe 50 or 100 sites that could accommodate these large instruments. There's a really important thing we've been taught by bad experiences and some good experiences. History of the land will play a pivotal role in this project. This is a map of the tribes that I don't know how complete this can be. It's one map of the tribes that represent the indigenous peoples of the United States. We'll have the opportunity and the obligation, that's clear, to work with indigenous people. You really want to incorporate them into our project, make it so that we're jointly putting this thing together in a way that will be constructive to their communities and constructive for the scientific communities. I think it can be a win-win situation. It's probably not going to be a simple one sociologically. It will be something that we'll all learn from, and we're going to try and share that knowledge so that future activities of this scale take place in a friendly environment. Then one last page, space. On the ground, you're ultimately limited by the seismic noise. You can measure signals down to 2 or 3 or 4 hertz or something like that. So below that is just too noisy on the Earth. Make measurements at higher frequencies. The thing to do is to get the sensing system off the Earth's surface, far away from the Earth, and set it up as a measurement system which is free of that kind of distraction. Very optimistic dates here. It's probably going to be 2035 that all of that's happening. The basic idea is similar to the one that we have in LIGO. We've set up a set of 3 satellites, which are in their own little pinwheel orbit around following the Earth obediently. And we measure the distance between those satellites using laser light. It's not exactly the same technique that we use in LIGO, but it's fairly similar. And with that, we can see the deformation of that triangle as a gravitational wave passes and record it. Some things I haven't gone into and probably don't really have the time to explain, but The lower in frequency you go, the bigger the masses that you can sense. And with this very long arm, it's like a radio wave. You have to have radio waves that match the lengths. The gravitational waves that match the length of LISA, the ones that come from supermassive black holes. Instead of these little things that we've been fooling around with that are only 100 times the mass of the sun, this is more like 1 billion times the mass of the sun. Take 2 billion mass black holes, which are like, I don't know how you describe 2 Death Stars, far larger actually, and spiraling slowly into each other, smushing together, and they shake space-time. That's the kind of thing that LISA will be seeing. And again, you can have ground observatories and space observatories looking at electromagnetic signals from these events and drawing enormous amounts of information from this combination of the multi-messenger signal sources. And this is planned to launch mid-2030s. So that's my story. I'm sticking to it. We start out with 2 black holes, which is 1.3 billion light years ago, and about the same time we were getting started here on Earth with life. We jump forward to Einstein's time, who could envision how this kind of system could work and how you could detect it, without having any of the technology or any of the information that we currently have about the universe. Phenomenal. I love this photograph because it looks like he knew exactly how this was all going to go down. Right? And so we ended up then with our discovery in 2015 and what we think is a great path in front of us for the future of this field. Thank you.
If you have questions, please raise your hand and we'll be happy to.
I have to ask you to speak up. It's not only masks, but I'm also hard of hearing because I'm old. So,
what frequency or frequencies of laser light does LIGO use? And can you say a couple words about how the beam splitters work?
yes. So the laser light that we use is 1 micron. So it's about 1/10 of the thickness of a human hair for the wavelength. It's in the infrared. You can't see it. We sometimes double it to the green for some other purposes. And it's sort of a 50 to 100 watt laser, extremely stable in intensity and in frequency and so forth and so on. And then, I'm sorry, your other question was?
How do the beam splitters work?
It turns out, well, usual way that you make a highly reflective mirror is put down multiple layers of different materials that have slightly different indices. And normally for a highly reflecting mirror, you put down 100 or something like that. Turns out if you put down just a few, then you can get something which accurately transmits 50% and reflects 50%. The 2 beams separated and recombine at the same place on the same beam splitter, both times getting that 50% split.
But then when they coming back, don't they split again?
And they do, in fact, but it's controlled. If you think about the Michelson interferometer plot that I've got there, when it's dark at the output, all the light's being reflected back to the laser. When it's light at the output, then all the light is just disappearing into this black hole. Add more mirrors there, catch that returning light and send it back in again. It recycles within that interferometer to increase the circulating light. In fact, hold the system very, very stably at a point just a little bit away from the dark. The output, watch tiny changes in intensity, and then try to keep as much light as we possibly can inside the system, circulating around and around to increase the sensitivity.
Thank you.
In an electromagnetic wave telescope, a spectroscope can add a lot of information. In a gravitational wave telescope, is there something analogous to a spectroscope?
It's a bit different. The electromagnetic telescopes are sensing power, and that power comes out and it can then be further resolved into its different spectral contents. In the case of the gravitational wave antenna, sensing the amplitude, it's actually the strength of the signal. So in this plot, we effectively have all the colors that are encoded. If we take this plot, we move from a time plot to a frequency plot. What you see is a bit of this lower frequency stuff at the low end, a big peak in the spectrum at this particular point here, and then at this very highest point, the spectrum falls off again. Effectively, the time series, the points of amplitude versus time, can be converted into the same kind of spectral information that you use from electromagnetics. Turns out this is a very nice format for comparison with series models, because all of the numerical relativity calculations for how these things move around, obeying general relativity and so forth and so on, they like to put out as their signal this time series. You can slap that up against here and see how you're doing in terms of a match. So the very fact that we sense amplitude also means that our sensitivity improves more quickly than a radio telescope does with sensitivity. It's a different way. You could, enough said, I think. Please.
Two questions. And
do speak up.
two questions, and forgive me if you answered these, but one, what is a graviton, and what is the advantage of even thinking of these space-time shifts as a graviton?
Oh boy. Now I will give my usual caveat. I build instruments. The gravitational wave has this duality also with a particle. The number of particles, gravitons in our waves is so incredibly high. I don't know what the number is, 10 to the 20 or something like that. We can't make any resolution of individual gravitons in any instrument that we can conceive of building. But it can be useful, I think, for theoretical studies. Sanjay, I don't know if you want to say anything about that. Do you have enough insights into the difference between gravitons and?
I can add a little bit to it.
Do please.
Just like when you have light, we can think of large numbers of photons that are contributing to a wave of light, and you can't really resolve the single photons. In these waves, there are so many gravitons that we think must be making up this wave. But to have instruments that can detect gravitons, that's not even conceivable at this time. So to think of these as classical waves is adequate for extracting the physics, and it's adequate for detection. But ultimately, we think there should be an underlying particle-like nature to this, which is predicted by quantum theory of gravity.
So it's a whole nother field and a very exciting one. And do you had a second question, or are you?
Well, the other one was more just why, how can this exceed the speed of light? How does that?
How can
the detection of this is apparently preceding the speed of light from the same.
Yeah, let me say a bit about the speed of light. Einstein had predicted that these waves would travel at the speed of light, but it was only a supposition at that point. The proof for us came when we saw a gravitational wave, 1.7 seconds later, the gamma ray. That meant that these two waves had traveled over these 1.4 billion years of travel through space. And because they're both influenced by massive objects along the way, they didn't take a straight line. They took some kind of crazy roller coaster, who knows what the amplitude of it was, to arrive. And they arrived within 1.7 seconds of each other. And so first off, you can say, well, even if there's a difference in the speed of light, it's incredibly small. It's 1.7 seconds over 1.3 billion years. And now, in fact, people go a little bit further and say, let's take that as a point of departure. Let's think about what astrophysics you can learn by saying gravitational waves are first produced, and then 1.7 seconds later, the gamma ray is produced. What does that mean about the way that jet evolves and how the energy escapes? That's our thinking on this.
Might not be at the exact same time.
That's right, but the difference in distance is, it's tiny compared with the total distance. It's the right way of thinking about it. So, in the back, please.
Since you're the builder, when you're doing site selection, how does seismic activity history affect your choices?
It's certainly one of the things that we look at. We look at the seismic activity to understand how much engineering work we'll have to do to suppress it. I can say a little bit more about that. In addition to just looking for a quiet site, you can also do something which is a bit more dramatic, which is to bury the detector deep underground. Because most of the seismic activity is in a really thin, kind of 500-foot, 1,000-foot shell around the outside of the Earth. And if you can afford to tunnel, you can reduce that noise. In fact, our European colleagues building the Einstein telescope and to bury their system. It's convenient in Europe because it's hard to find a place where it isn't covered with people and cows. But that's not what we're planning on doing in the US. And it's because we are making this scientific trade. We're saying we're willing to deal with a bit more seismic noise, some small compromise in the kind of science you can do, to be able to build a longer system, which will have an easier time getting a good sensitivity. There isn't really a right or wrong here, but it's how you choose to put your prioritization, the way that you put it together. So we like bedrock, and we like to attach ourselves to something really firm. We like to be far from the oceans because they're getting pummeled all the time with water. There's every 1.6 seconds, there's another ocean wave somewhere that crashes. We want to avoid places which are seismically active, clearly. We're not necessarily in those situations right now with our current detectors, the one up in Hanford. But there are a whole bunch of criteria that we use to try and select a good site. Selecting a site's complex. But, yeah, please.
So on a stat plot, how many of those of the detections were neutron star collisions?
Oh, you know, I should know this number by heart. I think we have something like 4 or 5 neutron star collisions. So we have that sort of number, you know, like of 80 or 85 or something normal ones and 4 or something like that, neutron star ones. We also have at least one neutron star black hole pair.
Oh, wow.
And so that gives us yet another kind of signal to look at and ways to analyze it. And then we have, in addition, one which resists classification. You expect if the star that's collapsing greater in mass than 1.4 solar masses, it can't resist its gravitational pull and it will collapse down to a point, black hole. We have one, but there's this kind of gray area between that. If it's in 3 solar masses, it's not going to collapse. We have at least one event which is in this gray area. We don't know if one of the 2 components is actually a black hole or a neutron star when it was going in. I'm looking forward to seeing more exotica like that. That's the fun stuff.
So do you know the result of the neutron star and the black hole?
We have the same kind of time trace, and with that we can calculate the masses of each one of those 2 objects and make some inferences about the neutron star. One of the great tricks that we want to do is to match up the theorist's prediction of the waveform extremely precisely with our measurements, and from that make inferences about how stiff the neutron star material is. And it turns out having a neutron star black hole, you have to have a very special ratio of those 2 masses if you want to learn anything new about the neutron star from that. The best measurements we have so far from 2 neutron stars coming together, we can see it's pretty stiff and there are some crazy theories that are outlawed, not very many yet. We need better detectors.
Well, it seems to me that it has to be so accurate with the waves being that small, and they have to match up when they return. Is there a system you have in this instrument that dampens out some of the seismic, or even like a airplane going overhead, or any of those kind of things?
We do a lot of work on that, yes. The LIGO instrument starts out in a fairly quiet place. And then there's a hydraulic system that positions a couple of tons of the vacuum system that contains all of this stuff. Then there are 2 layers of systems where for each direction, there are these 3 perpendicular directions, X, Y, and Z. And there can be translations along any of those 3 axes. There can be rotations along any of those 3 axes. You sense all of those with very careful accelerometers, develop an electrical signal and send it back to a motor that says, don't move. And so we do that on one platform, a 6 degree of freedom stabilized platform. We do it a second time, increase the isolation. And then we make a cascade of 4 pendulums. And you know, if you have a pendulum, here's my pendulum bob, and here's the support point. I move it very slowly, the pendulum bob is going to move with my support point. If I move this support point quickly, the mass wants to stay where it is. It has inertia. So that's a form of seismic isolation, which is extremely low noise, pretty darn good. And if you pile those one on top of the other, the effect multiplies together. Net result is at the frequencies where we're trying to measure, we're measuring in part 10 to the 20 of motion. and the ground is moving at 1 part 10 to the 10, suppressed by 10 billion, the level of noise mechanically that's transmitted through. Let me come back to your airplane. So we can do a good job of getting that seismic noise out of the way. Airplane's a different matter. Here I am, here's this mirror, which is suspended as a pendulum, and it's hanging for what we call the center of the Earth. If I put a really big airplane right over here, there's actually, thinking about like in the Newtonian sense, some attraction between this airplane and my mass. The mass moves a little bit over in the direction of the airplane. So as that airplane passes, mass goes, that I cannot distinguish from a gravitational wave. It's a noise force for us that we can't shield, can't reduce it. If you go underground, it's another good reason to go underground, we'll have less of that effect from ordinary seismic activity and from changes in atmosphere. You can't shield it. That is ultimately, that's the long explanation for why you have to go to space. You want to go to really low frequencies. You can get to the place where there's no mass nearby, and that effect becomes negligible.
So the new one is 20 miles long as opposed to 2.5 miles. That must be like 10 times as hard to.
Well, it actually, everything gets 10 times better. When an airplane goes by, the mass moves, let's say, by an inch. And that inch on a short system it looks like a much bigger disturbance than an inch does over the 40 kilometer to 25 mile one. All of those noise sources, they all stay the same. And my signal gets 10 times bigger. It's a real good sheet. All you have to have is on the order of $1 billion.
What do you about noise and quantum uncertainty?
We spent a lot of time on that. First off, we try to increase the amount of light that's circulating as much as possible. The photons arrive at a random rate, and they make kind of like raindrops on the tin ceiling. And if you've just got a lightweight rain, it gives you a fluctuation, which pop, 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 pop. If you've got a really solid rain, it becomes a very solid, constant sound. So the trick is to use as many photons as we possibly can, so that averaging out that comes with a very high rate of arrival of photons is very uniform. The problem is that when we turn up the gain on our laser too high, it starts to actually shake the mass because the photons hitting the mass shake it. And so there's an optimal level of power in that kind of interferometer. And you can do tricks with photons to make them work better. I come back next year. I'll give a lecture on squeezed light, which describes the kinds of tricks that we can play. The Heisenberg uncertainty principle. Only look on one side of the Heisenberg uncertainty principle at high frequencies and at the other side on low frequencies. And in that way, reduce the effect of these quantum effects at all frequencies. Frequency-dependent squeezing.
From what is known of gravity, is there any evidence that your descendants will make a machine that can cancel gravitational attraction and have these float?
I think, well, first off, for me, that sounds very unlikely considering what we know now about the physical world. Again, I'm an instrument builder. I'm not a theoretical dreamer. And it could be there's some ideas that are floating around of which I'm completely unaware. It could ultimately do something. For the moment, though, this effect is so tiny, so tiny, and it requires such instrumentation now to see anything at all. It surprises me if we can make our tractor beams and all those good things that we see on TV. Maybe that's the last question, please.
So from my understanding, all of the detections of gravitational waves have been from these two-body orbiting systems. Are there any single-body events that are energetic enough to produce gravitational waves?
Well, there's one that I can, which is probably not the kind of thing you're thinking about, but yes, suppose you take that neutron star and you give it a mountain, a little bump on the side. All of these objects have spin. Whenever you build things out in space, they accrete matter, and when they catch some bit of matter, it increases their spin rate. And so you imagine this neutron star spinning around with a little mountain on the side, and that makes the kind of asymmetry that excites Einstein's gravitational waves. Because these neutron stars are isolated and so very stable, they spin at a very, very constant rate. And so what we do is to look, for instance, and they give off radio signals, which is a nice, really, really cool thing. They have magnetic fields that shakes electrons. So there are a bunch of pulsars that are known as frequency references. because there are these neutron stars that are spinning. We look at those frequencies to see if we see anything in our gravitational wave signal that correlates with the radio signal that's coming from the pulsars. So far, we haven't been able to see anything, but for a kind of fun number, we're now at the point for a number of neutron stars, which are distant by hundreds of millions of light years. We can say that there are no bumps greater than a couple of millimeters tall on neutron stars, because if they were any taller, we'd be able to see a signal. This is a factor of 10 better. We'll be down to tenths of a millimeter of symmetry, and starting to get at the point where theorists say these things must exist. And that would be an exciting thing. You can also use that to infer more information about the inside of the neutron. Okay, well, okay, one more question.
Do gravitational waves have a Doppler effect the way you have with light waves?
Absolutely. And in fact, to look at that kind of source, to do a lot of complex math, because not only is the Earth turning, which shifts the frequency, it's also rotating around the sun, which shifts the frequency. And so even though it's a constant tone, exactly A440 up there in space, it arrives here, it warbles between 443, 444, 445, 443. And for each point in space, you need to make the correction for that Doppler shift, which means that it's really hard to look at the whole sky. It's an intractable computational problem at this time. You have to select selected places if you want to do the best job. Okay, well, with that, thank you again.